Okay, so the first four problems are just to match the graph with the equation. And the key thing here is that the ways that we talked about transforming other parent functions like we did in chapter 1, the same thing apply for exponential functions. So you can see the parent function here is 2 to the x. And so if we were to draw that on, say, this graph A, 2 to the 0 is 1, so that goes right there. 2 to the first power is 2, so 2 to the first power is 2. And if you did 2 to the negative 1 power, that's 1 over 2 to the first power, which is a half. So this is what the parent function would look like. So one thing you can see here is that this one is shifted up 1, because if we follow this graph down, the red graph here for A, you see it approaches positive 1. So this must mean that equation 1 goes with A. Now all these others are shifted. They're not shifted vertically. Actually, 2 to the x is the parent function. So all we have to do is find one that looks like this, that goes through x equals 0, y equals 1. So this has to be C. This one still has the asymptote of 0, but it's shifted 2 units in the x direction. And remember, the x shift was in the argument of the function. So if we had x minus 2 quantity squared, we'd shift it positive 2, direction positive 2. So this thing has been shifted, so the argument is the exponent. So you can see the last one here is a shift in the x direction. And it's x minus h, so h is 2, which means it's shifted 2 units. So this is B. And then here we have a reflection across the, well, we have a negative sign in front of the x. So we have, if it was negative 2 to the x, then it would be flipped over the x-axis. But this is a y-axis shift, or a y-axis reflection. So you can see, compared to the parent function, it's shifted over the y-axis. So this one is D, besides the fact it's the only one that's left that we haven't done. Okay, it says use the graph of f to describe the transformation that yields g. So this is f of x, this is g of x. So again, this is just looking at the transformations associated with these functions. So what we'll do is we'll plot both of them. So you'll need a piece of graph paper to do this. So we'll learn about how you can plot these parent functions, and a lot of it has to do with just, what's the value when x equals 0, x equals 1, and when x equals negative 1. Kind of gives you 3 points. So here we have 3 to the x. So if we have 3 to the 0 power, you get 1. So all of these should go, in terms of the parent function, should go through y equals 1 when x equals 0, because any number raised to the 0 power is 1. Now this is the third, 3 to the first power. So if we go, if x equals 1, we have 3 to the first power, which is 3. And if we go negative 1, we have 1/3. So this is, you take the reciprocal of this base. So there you can see that that's what this thing looks like. If you had 2, you'd have 3 to the second power. So you could do one additional point here. Now here we have the transformation. This is a x shift, x minus h. So h is 4, which means we're going to shift everything 4 units in the x direction. So we could shift this point, the y-intercept. So we go 1, 2, 3, 4. We could put that there, and we have the same asymptote. But relative to this point, that it was the y-axis intercept, you see we went 1 unit to the left and to 1/3. So we go 1 unit to the left, 1/3, like that. Go 1 unit to the right of this kind of base, this anchor point, and you go up 3. So this was 1 unit to the right, up 3. You go 2 units to the right, up 9. And so the transform function would look something like that. Okay, next one, you've got 10 to the x. So again, you could do 10 to the 0, which would be 1. 10 to the first power would be 10. And then you'd get 1/10 right here. So it really goes up fast. Like that. So here what we have, remember you factor out the negative sign. So you have negative the quantity x minus 3. So what's going to happen is we're going to shift, we're going to do the shift first. So we're going to shift 3 units, positive 3 units, x minus h. H is, in this case, h is equal to 3. So we're going to shift this 3 units, this point, the y-intercept, 1, 2, 3 units, okay? Now, this negative in front of the argument means that we're going to flip it across the vertical axis. So our new axis is here at x equals 3. So instead of going to the right and up to 10, we're going to go to the left up to 10. So we're flip on either side. So this was to the right, this one's to the left of the new. And likewise, you go down here over 1, and you'd have 1/10. So the transform function looks something like that. We still have the same horizontal asymptote. Okay, next one, we're to the 3/2 power. So what's going to happen is you're going to have, when x equals 0, you're going to 3/2 to the 0, which is 1. When x equals 1, you're going to have 3/5, which is going to be about right here. So when x equals -1, you're going to take the reciprocal of that, which would be 5/3. So you have that. And then the question is, what's the next one? Well, if you think about it, if we had x equals 2, f of x would be equal to 3/5 squared, which would be 9/25. 3 squared is 9, 5 squared is 25. And the other way would be 25/9. So that's about 3.5. approximately. So we go over here 2 and up 3.5. 1, 2, 3, 4, 3.5, something like that. And then we go down here and you'd have 9/24, which would be about not quite 1/3. Okay, so you can kind of sketch things in. So what you see is that a negative exponent is kind of the same, results in the same kind of thing as a fraction. Instead of exponential growth, it's exponential decay. Now here you have the negative sign in front of the whole thing. So this is going to be a y-axis or x-axis reflection. So this is x-axis reflection. Here you have x minus the -4, because I want to put it in the form of x minus h. So what we're going to do is we're going to move this point here 4 units to the left. 1, 2, 3, 4, like that. But then we're going to flip it over the x-axis, so it really goes there. And so we can, again, relative to this point, here you went down to about there, so I'm going to go down to about there. And this one will go down further. Then to the left of here, we go up to, not quite, we go up to 1 2/3, 5/3. So that's going to be about right here, and then we went up to 1, 2, 3 and a half. 1, 2, 3 and a half. So this is the transform function, like that. So the negative sign here makes it flip across the x-axis, and it makes sense because you're going to get a negative result. This is going to give you a positive result, and if you take the additive inverse, it's going to make everything become negative that was positive. Okay, the last one here. So 3.6 to the 0 power is 1. So again, we go through here. 3.6 to the first power is 3.6. 1, 2, 3, 3.6. Then you have 1 over 3.6, which is going to be about right here. And so this is the parent function. Now 3.6 to the second power is going to be more than 10, so I know it's going to go up pretty quickly. Okay, so that's the parent function. Now what you've got is you've got this 8. So that's, you're going to move the move it vertically 8 units. So let's move this 1, 2, 3, 4, 5, 6, 7, 8. So that's this point. There's going to be no shift in the x direction. You are going to flip it over the x-axis. So our move to x-axis is going to be here because we're shifting everything up. So the x-axis moves up 8, and there's the point, 1 unit above the x-axis. But we're going to, because of the negative sign, we're going to flip this over to this side. So that's going to happen. We're still going to approach, this horizontal line, which is the x-axis shifted up 8 units. And then we'll come through here. Remember, this point was 3.6 units from the x-axis, so we're going to do the same thing here. 1, 2, 3, 3.6. So that's going to put us about right there, and then it's going to keep going. Now, if you did 3.6 squared, you could, relative to here, you could go down that many units. And I'm just going to plot this just to show you that it did work out, kind of how it works. We could do like kind of in steps. So let me just make this thing a little smaller so we can see what's going on. Okay, just want to make sure I could see. Okay, so the parent function is 3.6 to the x power. So there it is. Let's zoom out in the y direction so we can get to 10, and then we can zoom out in the x direction to get to 10. There we go. So you can see how that looks. Notice it goes through x equals 0, y equals 1, x equals 1 would be 3.6. Now, if I take that and let's just add 8 to it. What you'll see is everything gets shifted up. So this gets shifted up. So here you have the line y equals 8. Now, if we go now and put a negative sign in front of the 3.6, we'll have that happen. So you can see that's what we ended up with. So it has this horizontal asymptote of 8, then it comes through 7, because that's 1 down from 8, and then it goes down 3.6 units when x equals 1. And you can see that it matches up pretty good. So, okay, so just again, how do you sketch exponential functions? Usually the easiest thing to do is to just plot 3 points as a minimum when x equals 0, when x equals -1, when x equals +1, knowing the general shape of an exponential curve, knowing that it has an asymptote, horizontal asymptote on one side. You can kind of work out the transformations. Okay, then we have 3 examples of where you use exponential, where you have exponential results. So the first one is from continuous compounding, and what it says is that the amount in a savings account is equal to the initial amount, which we'll call the principal, times e to the RT. So P is the initial amount in whatever currency you want to do. We'll do dollars. So in our case, this is $5,000. R is the interest, yearly interest rate. And that's decimal. So we use the decimal form, not the percent form. So they tell us it's 7.5%, but the decimal equivalent is 0.075. So you take this number 7.5 and you divide by 100, and that gives you the decimal equivalent. And T is the number of years. So in that case, for our case, it's 50 years. So we'll say the amount is equal to the principal, 5,000, times e to the r, 0.075, times the number of years, which is 50. And if we put that into our calculator, so let's do e to that number first, and then we'll multiply it out. So we take e to the 0.075 times 50. So you get a multiplier of 42. So e to that, e to this given quantities, is times 42.52. So times 50,000, 5,000, and you get $212,605. So you start with 5,000, you end up with 200,000. So what this is showing you is that if you have a pretty decent return, 7.5%, you can take a modest sum and make it into a very big sum. Now, of course, 50 years, you'd have to be grandparents or something like that. Great-grandparents, put some money in there. This is actually somebody who's maybe wants to put a scholarship together. They're like, 50 years from now, I'm going to have this scholarship amount. Okay, next thing is looking at this, doing the average rate of inflation. Here we're to find the value after a number of years. You take the interest in decimal form and you add it to 1. So in this case, the base is not E, which is when you have continuous compounding. So this is yearly compounding. So you have 4% inflation per year, and each year you're going to pay 4% more above the previous year. So it ends up being this 1.04 for the first year, 1.04 times 1.0 for the second year, and so every year it increases. This is kind of this fights against trying to make money, save money here using continuous compounding. You're going to lose some of that benefit because things are going to cost more in the future. So this is my exponential equation. P is the amount that is presently valued. This reflects the inflation rate, 1 plus the decimal equivalent of the inflation percentage. T is the number of years. So it says the price of an oil change in your car is presently $23.95. Estimate how much it'll cost to have your oil changed in 10 years. And it's not a better oil change, it's the same oil change. It's just because of inflation. So you'll take 23.95 times 1.04 to the 10th power. And again, 4% each year doesn't seem that much, but if you take 1.04 to the 10th power, you'll get 1.48. So it's going to cost almost 50% more in 10 years. So you get $35.45. So that's C of 10. That's C of T, where T is the number of years. Okay, so that was pretty easy. And then the final one here is, it says a meteorologist measures the atmospheric pressure P in pascals at altitude H in kilometers. The data is shown in the table. A model for the data is given by the equation, which is an exponential equation, where the base is E, which is 2.71828. It says sketch a scatter plot of the data and graph the model on the same set of axes. Estimate the atmospheric pressure at a height of 8 kilometers. So the way we're going to do this, we're going to use Excel to do a scatter plot, and then we can also plot this. Now it says to estimate the atmospheric pressure at 8 kilometers, all we have to do is stick 8 into there for the height, and that'll give you it's an estimate because this model doesn't give these exact numbers. I'll show you how they come up with this equation. We'll see how close we get with this equation. So hopefully you have Excel, which you do have Excel because the college provides it. Okay, so here's Excel. And what we're going to do is make up this table. So this is going to be altitude in kilometers. This is pressure in pascals. Now you can change the width of these columns by going between them and getting that little arrow, double arrow, and stretch it out. Or another way is to put it between the two, between B and C, and then double click it, and then it automatically makes it so the width fits. Okay, so our numbers are 0, 5, 10, 15, and 20. 0, 5, 10, 15, 20. And these are the actual data points. So let's see if I can make this so I can see this without, so I don't have to keep. So I guess I have to make this thing smaller. Okay, just want to make sure I can see the data so I don't have to keep flipping back and forth. 101, 293, 54, 735, 23, 294, 12, 157, and 5069. So that's the actual measurements. So they said do a scatter plot. So let's show you how to do a scatter plot. So the best thing to do is to highlight these two columns. Go to Insert. Go over here to Charts. See this little scatter plot? Pick the one that's a scatter plot. And there you go. So that's the scatter plot. Now, they've given us an equation that supposedly fits this data. So what we can do is we can calculate the pressures based on this model. So the model is, let me write this down. So the model is 102,303 e to the minus 0.137 h. Okay, where h is the height. Okay, so here we're going to say equals, that's how you put a formula in, 102,303 times exp, so that's the exponential function, minus 0.137 times h. Instead of using h, we click in here for the altitude, right parentheses, so we do the exponential for the whole thing there. And you can see we're going to get, because altitude is 0, we're just going to get e to the 0, so you'll just get 102,003. You say they're not exactly the same thing, and that's because this is a model that's trying to fit the data as well as possible. So then you can take that equation, you can just copy it by clicking on this cell, grabbing the corner, dragging it down, and you'd see, these numbers are okay. So one thing we can do is we can now add this data to our plot. So we'll go over to the graph, click on the graph, then go to Design, select Data, and right now it's saying select the data is just these cells. So if we were to highlight all 3 cells, you can see now it says pressure calculate. And then so that's your y-axis values. These are your x-axis values. And so if we say OK, now you can see that it shows dots, brown dots for the calculated and blue dots for the actual measurements. Now if I click on the green dots, the brown dots, and then I right click, I can say, actually what I want to do is change series chart type. So there I could change it, it's still a scatter plot, but you can get a scatter plot with smooth lines through it. So that's one way of doing it. So if I say that, now you can, it's gone to change both of them. You can see how sometimes the brown line is below the blue line, sometimes the brown line is above the blue line. So the blue line is the actual data. The brown line is the equation. Now, one thing else we can do is if you click on one of the blue dots, you'll see how the blue dots get highlighted, and then right click, and it says add trend line. So what we want to do is we want to add an exponential trend line. And so this is the something you can do in Excel. You can add a model, which we're saying is exponential. And I'm going to also display the equation on the chart and say OK. So I'm done. Where's OK? I don't think anything. I just close this. So let's pull this thing up. So you can see this is their model they came up with, which is not exactly like this one. You can see how it supposedly it's just different fit. It's higher here. It's about the same there. It's a little bit lower there. So which one's a better fit, I don't know. So let's see, what the heck did they ask us in this problem? Sketch a scatter plot of the data, which we did. Graph the model on the same set of axes, which we did. Okay, and then it says estimate the atmospheric pressure at a height of 8 kilometers. So that's just a matter of evaluating this function at 8. And we look up here, just in the graph, it should be maybe around 30,000, because 5 is 54,000. and 10 is 23,000. So we're going to have 102,303 e to the minus 0.137 times 8. So if we take e to the negative 0.137 times 8, so this thing here evaluated is 0.334. So we multiply that by 102,303, and we get 34,190. The units are pascals, which we use PA, or I guess they're just using P for pascals. Pascals or pascals. Okay, so that's it.